Hi everyone, this is Advanced Statistics for the Social Sciences. In this lecture, we'll go through the steps of null hypothesis significance testing for simple linear regression. So to start, for thinking about null hypothesis significance testing for simple linear regression, we are comparing two models, the way that we've talked about in the prior data analysis framework. So we're going to have the compact model, or the null model, and we're going to have an augmented model, or the regression model. These plots show you the relation that we would expect between x and y for the null model and the regression model. So for the null model, we hypothesize that x has no relation on y. And so in this situation, if x and y are not related, we don't need to account for x in the model at all. And so the equation corresponding to this plot indicates that. We have no parameter associated with x in the null model. Now, if we look at the plot for the regression model, we see that x and y do have some relation, so that as y changes, or as x changes, y also systematically changes. This means that we would have to account for the predictor x in some way if we are modeling y. And so in the regression model, we have this additional parameter that corresponds to the predictor x, and that parameter is beta 1. So the goal of significance testing for simple linear regression is to compare these models, compare model C and model A. And as we just saw, model A has just one additional parameter, that's beta 1, and that is the parameter that relates x to y. It tells us how x predicts y. And again, we call it simple linear regression because simple means that model A has just one additional parameter as opposed to multiple additional parameters. So to recap the steps of null hypothesis significance testing, we start by stating the hypotheses, we then set a criteria for the decision, we compute the test statistic, and we make a decision. Now let's go through these steps using the smoking example that we've been working with for simple linear regression. The first step is to state the hypotheses. So these are what the hypotheses would look like for simple linear regression with this smoking example. The hypotheses revolve around that beta 1 coefficient. Now remember, we use the population notation beta because the hypotheses are stating what we think is true in the actual population, or true in reality. So for model C, we don't incorporate any beta 1 predictor, and that's the null hypothesis model. So our null hypothesis is that beta 1 is equal to 0. With this smoking example, the way we would interpret that is that if beta 1 is 0, then x does not significantly predict y. So we would say that the number of years smoking does not significantly predict the number of cigarettes smoked per day. The augmented model, or the alternative model, the regression model, does incorporate this parameter beta 1 to relate x to y in some way. Therefore, the alternative hypothesis is that beta 1 is not equal to 0. Now, if it's a non-directional hypothesis, we say beta 1 is not equal to 0. It could be negative, it could be positive, it's just not 0. We know that if this were a directional hypothesis, then we would say that beta 1 is either greater than 0, indicating that x positively predicts y, or we would say that beta 1 is less than 0, indicating that x negatively predicts y. But for the purposes of this example, let's just say that we have this non-directional hypothesis, and so beta 1 is not equal to 0. And if beta 1 is just non-zero, then we would say that number of years smoking significantly predicts number of cigarettes smoked per day in some way, either positively or negatively. Now, step 2 has traditionally been to state the criteria, and this is where we've talked about the rejection rule. Now, when we were computing statistics by hand, we had to go in and look up tables for critical values, but really for the criteria, when we're conducting linear regression, we're really just going to be using a software program. So we needed to know what our alpha level is, but really all of the software program, SPSS and R, do this for us. So we know that we typically use alpha equals 0.05. And the rejection rule would be to reject the null hypothesis if the absolute value of the observed B1 coefficient, the computed B1 parameter estimate, is greater than or equal to the critical value. And we never see the critical value because SPSS does all of this for us. So actually our rejection rule is really just looking at is to reject the null hypothesis by looking at the p-value from the computer output. So if the p-value for B1 is less than 0.05, then we reject the null hypothesis. Step 3 is to compute the test statistic. Now, I did show you the formula for the test statistic for B1, and it is calculated using the correlation between X and Y, and also the standard deviations of X and Y. And that calculation is shown here again. But when we run the analysis on the computer, we don't have to calculate this by hand. We can actually just find this in the computer output. And I've again shown you the computer output and highlighted that coefficient here. So it's under the unstandardized B column, and year smoking is the predictor, and you can see the little footnote on the table that says the dependent variable is number of cigarettes smoked per day. So that's kind of how you find it in that coefficients table. The next step is to decide significance, and we also look at the computer output for this. So remember, when we are running a software program to conduct this analysis, we reject the null hypothesis if the p-value associated with that coefficient or parameter estimate is less than 0.05. And I've highlighted the boxes where we can find the information for deciding significance. So the B1 parameter estimate is 0.738, and the associated p-value is in the column all the way to the right in that same row, and it's 0.113. So if we plug that into the rejection rule, 0.113 is greater than 0.05. So we will not reject the null hypothesis for this particular analysis. The way we would interpret this is we would say number of years smoking does not significantly predict number of cigarettes smoked per day. Now, let's talk for a minute about the conceptual interpretation of the results of this analysis. When we looked at the plot of years smoking and number of cigarettes smoked per day, the plot shows a positive relation. However, we had an extremely small sample size in this study. There were only 15 people in this study. And then our results indicated that the test of B1, the predictor, which related the predictor X, years smoking, to the outcome, number of cigarettes smoked per day, was not significant. So although we see some positive relation in our plot, in our initial plot, the results of our analysis indicate to us that these results are either due to sampling error or we could have inadequate power to detect this effect. This concludes the third lecture on linear regression. In the next lecture, I'll talk about proportional reduction in error for this model.